So now that we have gone through the theory of study unit 1 and 2, we can go through a couple of illustrative examples to see what sort of questions you can expect from the study unit. So this is one of the type of questions you can expect from the study unit. The first question would be a basic one, like what can name the topology. Is it series shunt, and is it transconductive, transimpedance, voltage, or current amplifier? So first of all, to identify the topology, we see that here we've got, at our input source side, we've got a current source. So then that tells us that this is shunt at the input, and here at the output, okay, and here at the output you've got a series loop, so that's series. So this makes this amplifier a series shunt series, my bad. Okay, and when you ask for the transconductance, when you're not sure of how to translate this into your voltage gain, your transimpedance gain, or whatsoever, so you can basically look at your output and your input. So at your output you have a voltage, what, VL, and our input is a current, IS, and that looks like resistance, which means this is a transimpedance amplifier. Okay, so that would be one of your typical questions. The second part of the question would be to calculate the overall gain, and a third part of the question would be to calculate the other types of gain, like you've got your current gain, your voltage gain, your power gain. But we're gonna start first of all by calculating our transimpedance gain, right? So to find out transimpedance gain, we need the loading factor for each stage, right? So for our input stage, we can see that because we've got a shunt here at the input stage, our loading factor is the current loading factor, which is RS over RS plus RI1. That's your input loading factor. Okay, let me actually do this on the new page. So your input loading factor would be RS over RS plus RI1, because here on your input side you've got current. You trying to get the ratio of current of I1 to the ratio of the total current, and that's it. And for your middle stage, your self-loading factor, it is Ri2 over Ro1 plus Ri2. That's a bad I. Ri2. So here we've got a voltage stage, so we use the voltage version of the loading factor, and we've got the same that's happening here. So output loading factor is RL over RO2 plus RL. So the values for these are 0.91, 0.5, and 0.99, right? So to get our overall gain of the system, you need to consider the gain here and the gain there. So our overall gain, A of G, no, it should be A of R. A of R is equal to the input loading factor multiplied by the gain A of RO multiplied by self-loading factor multiplied by A V of O multiplied by the output loading factor. And all of this gives you a value of negative 4.5 kilo ohm. You can punch in all the numbers and that's what you get. So we had found our transimpedance gain to be negative 4.5 kilo ohms, and this is equal to your output voltage over your input current. Now, as soon as you have one gain, it is quite easy to find the other gains by relating each of the gains via this formula. So for your current gain is output current over input current. So if you simply take your transimpedance gain and divide by the load, basically changing VL over RL is equal to IO. So that is how you would get your current gain from your transimpedance gain. It's A of R over R of L. And for your voltage gain is V out over V in, V source V in. So here in your transimpedance gain, you've got your current of source. So to get the voltage of source, you must multiply this value by the source resistance. So that would be A of R over R of S. And for your transconductance, A of G, it's your output voltage, for transconductance, I'm actually running out of space here. For transconductance, it is your output current over your input voltage source. So you would take your R of L, your resistive gain, and you divide it by R of L, and also multiply by R of S, because here you're trying to get the source voltage from the source current and you're trying to get your output current from your load current, your load voltage. So it's simple to get your other gains, your other four gains, from one of the gains, as long as you know the relationship between the gains. So to continue with this question, another question that could be asked here is to find the power gain, both in decibels and in watts per watts, to find the efficiency of the amplifier. Yeah. So those are the two things that we are going to find now: efficiency and power gain. Now our efficiency is output power over input power, right? Efficiency is always it is evaluated at the highest output of your circuit. So we know from this circuit, we know that our saturation of the second stage is 0.5 volts, and the power dissipated by the second stage is 50 milliwatts, and the power dissipated by the first stage is 5 milliwatts. We are not given any information about the saturation of the first stage, so therefore we are correct in assuming that the first stage does not saturate. Alright, so if you remember about how saturation affects your output, if that's your supply, VCC, your saturation voltage is here, Vset. Okay, so therefore this means that the peak voltage at the load is equal to 4.5 volts. Right, to get our power efficiency, we need to have our input power, so therefore we need to have our source current, and to relate our output voltage here at the load to our source, we are going to use the transimpedance gain, which we found A of R equal to negative 4.5 kilo ohms, and that is equal to the load voltage over the source current. So therefore this gives us a source current of 1 milliamp. Alright, so the power that is delivered when you're doing your power efficiency, you use average power, and what we've been working so far here is the peak, right? So we need to turn this peak into the RMS value. So this is I source of peak. So I source of RMS is 1 over square root 2 milliamps. Because to get the RMS value of a sinusoidal, you multiply it by 1 over square root 2. So therefore your input power in, is equal to I squared R of S in parallel with R of I1. This is because that is the power, the current is being delivered to both of these. So using that, you've got an input power of 45.46 microwatts, right? And your output power output is, you can use V squared over R of L. Remember to also turn your 4.5 volts peak of load to RMS. by using this formula. So this is the V you're going to substitute into there, and then you're going to get your output power to be 10.13 milliwatts. Alright, so this means that your power efficiency will be next page. Efficiency is power out over power in, which is your output power was 10.13 milliwatts, and your input power consisted of 5 milliwatts and 50 and 5, and this 45.46 micro. And that gives you an efficiency of 18.4%. Right? And that is how you calculate the efficiency of your amplifier. So for your power gain, A of power, you've got basically your power to the load divided by input power, which is 10.13 millis over 45.46 micro, and that gives you 222.79, right? And in dBs it is 10 log of this value, which will give you 23.48 dBs. And that is as difficult as you can get for this. And yeah, that's it. So there is more to ask to this question, and the other question that can be asked from this set of questions is for you to find the time constant associated with the input stage, with the self-loading stage, and the output stage. So these time constants are caused by these capacitors, right? So when it comes to these capacitors, you must remember that when capacitors are in parallel, that they add up, C1 plus C2, right? And the equivalent resistance seen between this node, as seen here, would be this one in parallel with that one. The same happens for this stage, where you've got R of O2 in parallel with R of I2, and the same for this stage of O2 in parallel with R of R. So that's something that's not too difficult, but this can be asked as a follow-up question to this. So for your input time constant, you would have R of S in parallel with R of I1, R of I1 multiplied by your CS plus CI1, that is I1, CI1, right? And for your interstage, you would have R of O1 in parallel with R of I2 multiplied by C of O1 plus C of I2. And for your outer stage, for your output, that would be R of O2 in parallel with the load multiplied by C out 2. So that's how you calculate your input load, your loading factors, and your answers are, for your input loading factors, 5.27 nano, 5.53, and 0.198. All of these are in nanoseconds. Your time constant is always in seconds. So the next question we ask ourselves is there a dominant pole within these three poles? So as we had discussed in the notes, the dominant pole is at least an order of magnitude greater than the closest pole to it. And when you consider the dominant pole, you only consider the first two poles. So first of all, we need to turn these time constants into frequency equivalents by using f is equal to 1 over 2 pi tal of I. No, it's not tal of I, it's just time constant. So for your input time constant, you've got a cutoff at 30 megahertz. For your self-loading, you've got a cutoff at 3 megahertz. And for your output, you've got a cutoff at 803 megahertz. Now, it is clear that this time constant of the self-loading factor is the pole of the self-loading factor is the first pole, and the next pole happens there at 30 megahertz. And there is an order of magnitude, as you can see, that your poles differ by a factor of 10. So therefore, your self-loading pole is your dominant pole. And that's pretty much it about how this section goes. As you can see, there's not much to it. This is the simpler version right before feedback. And yeah, that's it.